Yeah, so I'm Rory and this is Eryn, and we will be taking you through the Creative Computation course over the next week. So we're going to start right at the beginning with, kind of how do we code in Wolfram Language. If you're, able to code in Wolfram Language already, then this will be a nice refresher, and give some nice keyboard shortcuts and menu options for you. And if you're brand new, then this should help you get started. So I'm gonna play this video, and the way that we're gonna go about this is we're gonna play the video, and then we're going to run through one or two of the exercises in the exercise notebook, and kind of live code those. And then we're going to have a poll question for you guys to engage with. So with that, we're going to watch this video. Thank you.
Hello. So, welcome to the second lesson, where we're going to talk about how we actually code in Wolfram Language and how we use a notebook. So, our learning objectives for this lesson are that we should be able to organize our text and code using Wolfram's notebook environment. We should be able to identify correct syntax for Wolfram Language, and we should be able to search for information in the Wolfram documentation. So let's start out with notebooks. What's a notebook? Well, we run all of Wolfram Language in a notebook environment. So that means that we can use a notebook, like the one that you can see right now, to code and also to create interactive documents. Notebooks are made up of cells, which is what we call each little piece of the notebook. These cells can have text or code, or they can be output cells, which is the output from the code. So there are a lot of basic things that you can do, just like in a normal word processor in a notebook. So a lot of these things, as well as other important parts of Wolfram Language, you can do faster using a keyboard shortcut. So we're going to jump straight to learning our keyboard shortcuts instead of doing it from the edit menu, because it'll make it much easier in the long run. You do a keyboard shortcut by pressing multiple keys at the same time. So you'd hold down the first key and hit the second key with your next finger. The first thing that we're going to do is find out what cell we're in. So you can, if you hover over your notebook, then you can see that your cursor changes from a vertical to a horizontal cursor. If your cursor is vertical, then that means that you are hovering over a cell. If you click it, then you'll get a black flashing line, and that'll show that you are inside the cell that you want to be in. If you're hovering in between two cells, then your cursor is going to be horizontal. To create a new cell, you click in between those existing cells when your cursor is horizontal, and then you'll get this grey line with the plus button on the side, and you've created a new cell. So if you just type, then you'll write code, and we'll get into that in a second. In order to make a text cell, then you hold down your command button, and it might be different on your computer, but whatever you use for normal keyboard shortcuts, for like copy or paste, you would hold down that command button and press the number 7 on your keyboard. And now you have a text cell. So if you type, then you'll get text. You can experiment with the different styles that we have available built in, and those go from command 1 gets you your big title header, and then 2, 3, 4, 5, 6, and 7 get different levels of headers or text. To get a bullet point, you just click into make a new cell, and you do Shift 8, and that gets you a bullet point. To make a new bullet point, you just press return, and then you get a new bullet point, and you can tab inwards by hitting tab. Fantastic. So now we can write text within a notebook at any level of heading. So before we move into code, let's have a look at cell groups and cells. So each grey bracket on the right side of the notebook represents a cell. Cells can be code, can be text, can be images, can be whatever you want them to be. You can select a cell just by clicking on that grey bracket. If you click it, then now your cell is selected, and you can delete it or copy it or whatever you want to do with that full cell. Titles will automatically create a cell group. So if we look at the bracket on the right hand side of this notebook, you'll see layers of the grey brackets going along. And you can see that the text and bullet cells under the section heading are all included in the group. So that means that you can select or copy or delete entire sections at a time by clicking on the far right bracket that encompasses the ones that you want to select. You can also close a cell group by just clicking on its bracket twice, and this will hide the cells in that section and gives you this nice little arrow button that you can use to reopen the group. So now that we've learned how to use a notebook as a text editor, as a word processor, we can also use it for code, which is kind of its core purpose. So if you type directly into a new cell in a notebook without using any of the text styles that we talked about above, what you type will be interpreted as code. So for example, if we type 2 plus 2, that's code. We can evaluate this code by making sure that our cursor is in the cell that we want to evaluate and hitting Shift Return. We can also select multiple cells on the right using the grey brackets to run multiple cells in a row. If you want to evaluate an entire notebook, you can do that from the evaluation menu at the top. If you just choose Evaluate Notebook, then it will run each cell in order from top to bottom. Cells evaluate in the order that you run them, and if you want to stop an evaluation, you can either hit Command period, or you can select Abort Evaluation from the evaluation menu. Cool, so we've learned how to type code, but how is code structured in Wolfram? Well, a large portion of the Wolfram language is based on a functional paradigm instead of being an object-oriented language. In simpler terms, we code by building up different functions and operations on a small set of data types, instead of using a small set of functions on new types of objects or data that we define. To use functions in Wolfram language, we follow the same structure each time, the same syntax, which is capitalized name of the function, open square brackets, the arguments that we're including, and close square brackets. So let's find the square root of a number as an example. So the function for finding a square root is square root. So we type that with a capital letter, and we open our square brackets, type the argument that we want, in this case 9, and then close the square brackets. If we evaluate that code, then we get 3. A lot of frequently used operations have a shorthand or a shorter way to write them. So we've seen already that 2 plus 2 evaluates to 4, but all of our math operations have a full form. So we can see that if we type plus, open square brackets, 1, comma, 1, close square brackets, then we get 2. And we can do that exactly the same thing with times and power and all kinds of all the math functions. And there are loads of short forms available for various functions that we will come across as we encounter each function. We'll also talk about its short form, and that can make your code shorter and easier to read sometimes. Let's talk about syntax coloring. So there are a few things that the notebook front end does to make it easier to visually see syntax issues or changes when we're writing code. So starting with symbols. If we see a blue symbol, that means it's undefined. There's no information saved to it. So if I just type hello, then Wolfram doesn't know what to do with that. So it's blue, it doesn't mean anything, it doesn't have anything saved to it, it's undefined. If we see a black symbol, that means it is defined, like a built-in function name. So for example, we can see that plot is defined here. Wolfram knows what to do with it, everything's good. If I tell Wolfram that hello is equal to 5, and then I run that line, then now it knows what hello means, and so it turned black. So now if I run hello separately, then it says, I know what to do now, it's 5. Some more syntax highlighting stuff that we'll get much more into as we go through this course. If we see a symbol that's green, it means that symbol is being used for a local variable. So instead of being in the whole notebook, it's just in this line. So in this case, x is 3, but only in this line. X is not 3 everywhere else. If we see a teal symbol, that means the symbol is being used in a very special way by that function. So for example, the table function will make things teal when they are being used in the special way within this function. Outside of just function names, we can also see when operations are missing or incomplete. So brackets without their pair will turn red, and missing arguments will be indicated with a red arrow. And since Wolfram uses the functional paradigm, we'll often find ourselves nesting functions inside of other ones. The function and the brackets that our cursor is currently inside will highlight in yellow so that we can keep track of where we are as we're writing code. So if we click in different places through this piece of code, we'll see which parts highlight. We'll be able to see the function and the brackets that contain the arguments of the function as we click on them. The last thing we want to talk about is autocomplete for code. So if you start typing in the name of a function, Wolfram will find the function that you're looking for and give you a list of potential functions that you might mean, and you can hit tab or enter to select that function, and then the whole thing will appear, so you don't have to type the whole name of the function each time. The syntax highlighting makes it much easier to write code, makes it much quicker, and can be really helpful when you're trying to read or write your code. So the most important part of learning to code is learning how to look things up. Even very experienced coders and scientists look up how to do things in documentation. It's way more important to understand what you're doing and what you need to find out than it is to memorize exactly how to solve a particular problem. This means that you'll be able to solve lots of different problems as you move through your coding experience. Wolfram Language is particularly well documented. So if you go to Help in the toolbar and click Wolfram Documentation, then you can open the documentation, which is organized by topic, so it's really easy to find what you want. You can search for a particular function in the search bar, or you could search for a task that you want to do in the search bar, and it will give you relevant functions and also tutorials and guides and toolkits for figuring out problems that you're trying to solve. If you've already typed some code and you want to look up a function, you can highlight it and press Command-Shift-F, and you'll be taken straight to the relevant page in the documentation. You can also hover over the function with your cursor and click the little eye symbol, and that will take you straight to the page. You can also get a brief summary of the documentation by using a question mark before the function. That gives you this nice blue box filled with information about the function. And again, you can click that little eye if you want to see the full page in the documentation. Amazing. We have reached the end of the second lesson where we've covered the basics of how to write code in Wolfram Language. So our key takeaways from this lesson are that notebooks let us create interactive documents made up of text and code. We can organize our notebook using cells and cell groups. We can write code into code cells and evaluate them by pressing Shift and Return. Functions in Wolfram Language all have the structure, capital letter, name of the function, open square brackets, and then your list of arguments separated by commas, close square brackets. Syntax highlighting is really helpful, and while we code, parts of the code will change color or be highlighted depending on cursor placement, missing arguments, or whether a symbol is defined. When in doubt, we should reference the Wolfram documentation. We should always be in there figuring things out and looking things up, and it's a very helpful resource when you are coding. Not just when you're learning to code, but also as an expert, you will have the documentation open all the time. Okay, and that wraps up lesson 2, and we'll see you next time.
Awesome. So let's do a couple of polls. You should be able to see now a nice little poll. Notebooks are made up of what? Which can be text or code. We had 96% of people chose cells, which is the correct answer. So well done. Yeah, notebooks are made up of cells, and they can be text or code or images or maps or 3D outputs or interactive outputs. Really anything they want to be. And that's kind of what makes up a notebook. How can you access the Wolfram documentation from a notebook? So Wolfram documentation is super helpful. It's I've coded in a lot of languages, and Wolfram documentation is pretty much the best that I've ever seen. It's always impresses me. But how can you get to it from a notebook? Okay, fantastic. So almost everybody picked that all of the above was true, and that is the correct answer. You can get to the Wolfram documentation from a lot of different places, in a lot of different ways. You can click that little eye, you can do a question mark, you can Command F Command-Shift-F will open it up. You can open it from the menu, and it's pretty great. Okay, last question for this video. What is the correct syntax for a function? What kind of brackets do we use? Where do we put the function name around our code? How do we use a function? Excellent. Looks like we got 100% agreement on function, open square brackets, argument, close square brackets. Perfection. So well done. Okay, so now that we have covered the super basics, we're going to move into some slightly less super basics, and I'm going to hand over to Eryn, who's going to lead us through the rest of the videos in this session. So, thank you.
Awesome. In the first, we're going to kick off with the next section of variables and functions and start to get some code we can start building out. First section of this course, we're going to build up our basics before tackling our first mini project on computational art. This chapter of the section will cover how we can use functions already built into the Wolfram language, as well as how we can use functions like set and setDelay to work with functions and variables we define ourselves. There are a lot of built-in functions in Wolfram language. This lets us get off to a quick start with a lot of basic computations once we understand the basic syntax for using a function. Since we're working with both built-in functions and, later in this section, our own functions, it's useful to know how to tell the two apart. Let's look at the example of list-line plot. Built-in functions are often, though not always, a word or sequence of words. They'll always start with a capital letter and have every other word capitalized. Built-in functions will also show up as black as they're defined. Undefined functions and symbols show up in blue. So if you're using a built-in function, but the function name is showing up as blue, check to make sure you don't have any typos. Functions within Wolfram will have the same basic syntax regardless of whether they're user-defined or built-in. We use the function by writing out its name, then putting the inputs we want after the function name inside of square brackets. These arguments could be anything, but most functions will have a specific input type for the different arguments. Instead of square brackets, we can use the @ symbol before an argument, or we can use the double slash to write the function name after the argument. These can be useful when we have quick computations we want to do with only one input. But most often, we'll want to use the square bracket syntax, as it's usually easier to read and also easier for use with functions that have multiple arguments. We've now covered how we can use built-in computations, but what about making our own? To get started, we need to understand how to define things in Wolfram language, which starts with the function set. We could write out the full form of a set like any other function, but we'll almost always use an equal sign. In our example, we write the symbol we want to define on the left of the equal sign, in this case x, and what we want to save to that symbol on the right. When we evaluate that code, the symbol will turn from blue to black, so now we know it's defined. We can then use that symbol to return the value we've saved. We can use a combination of letters and numbers to create variable names, but one common convention that's useful to stick to is not capitalizing the first letter. This makes it clear for both the computer and anybody reading the code that it's a user-defined variable, and we won't run into any conflicts with built-in symbols. setDelayed, which is represented by a colon followed by an equal sign, is another function that lets us save information to a symbol. However, setDelay does not immediately evaluate what we put on the right-hand side. Instead, we're saving that expression or piece of code to the variable, and then that code will evaluate later on when we call the variable. It's a little bit easier to see in action with some of the built-in functions that give random outputs. For example, each time we run the function random color with no arguments, we get back a different random color. If we use set to save the function random color to a variable, it will save the output from random color on that first evaluation of set, and every time we call the variable, we'll get that same color. If we use setDelayed instead, we'll be saving that chunk of code with random color to the variable.
And that code will then be reevaluated every time we call the variable. This means with random color, it'll rerun that function each time and return a new color every time we call that symbol. Now that we can save a piece of code to a symbol, we can define our own functions. We'll be using the following syntax with setDelay to create our own functions. We start with a function name. Let's say the letter f. The function f is going to take some arguments that we put within square brackets. Let's say that f has one argument x. This argument name x is a placeholder, so while it's useful to make it a variable that makes sense with what it's representing, it could really be any symbol. After the argument x, we write an underscore, which we call a blank. Later on in the course, we'll talk a little bit more about what blank is and how we can use it. For creating our own functions, we mainly need to know that blank indicates any one thing. Together, x followed by a blank means that our function, f, takes in an argument that is any one thing that we're going to represent with an x in our definition. We're going to just use one argument for the function f, so we can then write out our setDelay with the colon and equal sign, and then whatever piece of code we want to save to f. We run our cell, and now we have a function. We can then give it an input, let's say 2, and get the output from our function for when x is 2. We can use this same syntax to create functions with multiple arguments by simply adding more arguments within the square brackets with different names. Let's add in the argument y to the function f, and now we have a function with 2 arguments. In this chapter, we've covered a really core skill for working in Wolfram Language. Before tackling the exercises for this section, you should now know how to use a function with square brackets, and know that you could also use a double slash or an @ sign. You've also seen how set lets us save information to a symbol, and setDelay lets us save a piece of code that will get reevaluated to a symbol. And, as we just covered at the end of this chapter, you now know the basics for defining your own functions using the general syntax of functions setDelayed and blank.
Awesome, fantastic. So let's do a quick poll. So what is the difference between set, which is equals, and setDelayed, the colon equals? So yeah, the colon equals sign. So the difference between set and setDelayed. So those options are: setDelayed saves a piece of information to a symbol, while set saves an expression or a piece of code to the symbol. Set saves a piece of information to a symbol, while setDelayed saves an expression or piece of code to the symbol. And there is no difference between set and setDelayed. So, yes, the majority were right. Set saves a thing that is already evaluated, doesn't need to be evaluated. And setDelayed saves a piece of code to be evaluated whenever we call it. Okay, so Eryn, do we want to run through an exercise from the exercise notebook?
Yes, absolutely. Let me just share my screen for this. Great, so we're going to do one of these activities, and we're going to look at defining a function, because this will come up a lot later on. So let's work through this. So we need to define a function that takes an image and blurs it. Well, first off, we should figure out how we...
Eryn,
yeah?
are you able to enhance that just a little bit? Zoom in?
Let me bump that up.
Let's say maybe like 150 even, or... Oh, yeah, that's great.
There we go. Cool. Perfect. So hopefully this looks a lot better for you guys now. So let's take an image and blur it. So how can we blur something? We go and look at our documentation page. Let it boot up for a second. Let's just see if we can find anything under blur. We look up and we see there's a function blur of an image with a blurred version of the image. So we can just use that. Super easy. So we only will do blur. Let's not look at that quite yet. So we can do blur, and then we'll grab our image from up here. That way we don't have to go hunting for one. Properly this time. Pop it in. Great, and we've got a blurred image. Awesome. Now to turn into a function, as we can kind of see from the spoiler of the solution, we got to use our set delay. So we'll title the list blur, and then we need to pick what our variable is going to be. In this case, let's use image. That'll make a lot of sense to anybody looking later. We do our underscore after our variable. We do our set delay, and then we do our code. Now, instead of using this exact image, we use our variable. We run this to save our function. And then if we try this again using our image, use the original one, we'll get our blurred image. We made a little function for ourselves. So hopefully you guys are able to follow the steps of that, figuring out the actual code first, and then all of this syntax here with defining a function.
Fantastic. So we're going to talk now about list, table, and map.
Continuing the first section of this course, in this chapter we'll be covering some core functionality for working with lists. We'll learn how to create a list with functions like range and table, how to generate visuals for different types of data. We'll cover how to also operate on a list with table and another function, map. And in conjunction with map, how we can construct and use what's called a pure anonymous function. Before we get to creating and working with lists, we need to know what a list is. Just like outside of computing, a list is how we collect things. In Wolfram Language, we indicate a list with curly brackets and separate each item in a list with a comma. We can make a list of almost anything, since it's a way to store elements and doesn't actually have to do with the elements themselves. So we could create a list that has numbers, strings, symbols, colors, images, and more. Later on, when we start to actually operate on lists, though, it'll be important that we know what type of data we're working with, and therefore what operations make sense. The list by itself, though, doesn't care what type of data we have. Now that we know what a list is, let's make a list. There's a lot of functions in computations where we'll end up with a list as our output, so in this chapter we're going to cover just a few basic methods for generating lists. Our first and probably most simple is the function range. Range creates a list of numbers based on our inputs. If we give range one number, it'll create a list of numbers from 1 to the given number, increasing by 1. So range of 10 will output all the integers between 1 and 10. We can give range additional arguments to generate other lists of numbers. If we give range 2 arguments, the first argument is the starting number, and the second is the ending number. So range for 4 and 10 will give us the numbers starting at 4 going up to 10. We can add in a third argument that is our step or increment size. This is how much we increase between each number. If we set the step size to 2, we can get a list of numbers from 4 to 10, increasing by 2 for each item in the list. Another common and more flexible way to create lists in Wolfram Language is with table. Table will repeatedly execute some piece of code, usually changing a variable we indicate each time it runs, and return a list of outputs for those repeated executions. If we just want to use table to create copies of an item, we don't need to include a variable. Our first argument for table is the thing we want repeated, and the second is how we want it repeated. If we want to create copies, our first argument is what we're copying, and our second is how many times we want to rerun that code. So if we set our first argument to the color blue and the second to the number 10, we can get a list of the color blue 10 times. Table is more flexible than range in that we can set a variable that we're changing for each evaluation. The first 3 examples of this work similarly to range, but with the addition of a variable. If we have the variable n somewhere in our expression in the first argument, we can then make our second argument a list, where we first indicate the changing variable and then what number we want that variable to go up to. For this example, we'll end up with just a list of numbers from 1 up to 10. Just like with range, we can add an additional specification to that second argument that shows what number we want to start at, and yet another to set the step size to a number other than 1. An additional feature of table is that it can iterate an operation through a list of items. So instead of giving table a specification for a number in the second argument, we can provide a list of values. It will then repeatedly execute the first argument for each item in that list. Often, when we're working with a list of items, it might be useful to visualize the list. There's a lot of different ways you can do this, and the methods you pick will depend on what types of data your list contains. If we want to organize information on our page, we might find it useful to put the list into a row or within a column. If we're working with numerical data, we may want some kind of plot. If we have a list of numbers, an easy one to start with is list plot, which will plot each number as a point with the x value increasing by 1. Bar chart is another data visualization that works in a similar way, but with bars instead of points. Most types of data will have some functions that work on a list of that data type. For example, word cloud is a great option for visualizing the frequency of words when working with strings. Image collage is one of a few ways you could combine a list of images into one visual. We've gone over how to create a list and how to make visuals from a list. What if we have some function, some operation we want to do to every item in a list? One option is to use table. Table can iterate an entire expression, so as I discussed earlier, we can use table to do more complicated expressions with a changing variable. We can also use table with multiple variables by adding a third argument with additional variable specifications. And if you do have multiple changing variables, table is likely the best way to iterate on an expression. As with earlier, if we're working with a list of items, we can iterate through that list by changing our variable specification from those changing numbers to that list. Another way we can apply an operation to every item in a list is with the function map. Map takes a function and will then use that function on every item in a given list, returning a new list. We can see this in action if we think back on what we learned in the first chapter of this section and define our own function. Let's define our function to be the same operation we just did with table. We can then use map to use this function across a list of numbers. Our first argument is the function, and our second is the list, in this case using range to create a list of numbers between 1 and 10. Map also has a shorthand, which is often used instead of the full form. When we use this shorthand /at, we put our function first, then our /at, and then the list we want to use that function on. When we're working with map, it's important to remember that map doesn't need square brackets next to the function. That's represented kind of visually with the shorthand, with the @ sign, as that's an alternative way to use a function instead of using square brackets. Map, especially with the shorthand, might seem easier than table, but defining a function every time isn't the most efficient, especially if we're only using the function once within our map statement. Instead, if we use a pure anonymous function, we won't even need to define a function. A pure anonymous function uses a slot instead of a specific variable like how we've been using n. We want to end our function with an ampersand. This indicates to our computer where the function ends. If we've constructed it correctly, any slots we've been using should turn from pink, an incomplete expression, to green, a localized variable. We can then use a pure anonymous function just like we would use any named function. Where the function name would be, we instead put the pure anonymous function. This means instead of using the named function with map, we can just use the pure anonymous function we've constructed. In this chapter, we've covered some pretty core skills for working with lists in Wolfram Language. You now know that we can create a list for any type of data, and that we represent a list with curly brackets. We can make a list of numbers with range. We can use table to iterate an expression, which can be useful when we're both making new lists and operating on existing lists. Map is another way we can operate on lists by applying a function to every element in a list. And we can use a pure anonymous function with variables as slots and ending with an ampersand to make using map even easier.
Awesome. So now we're going to do another exercise on this section. All right, cool. So we're going to blur some images because we already know how to do that. Super easy. We know that it's blur and then an image. So easy for us to get started with this problem. So we need to use table to apply blur to these images. So we have a list of images here. So we know we're going to use table. And our construction table is we'll have the thing repeating first, and then whatever we're repeating for second. So the thing we want to repeat is blur of some image. And our second argument is how that image is going to change. I have something saved to image, so I'll just clear that real quick. So we'll have something image changing, and we want image to change with these images. And we just learned that if we have a list of things we want table to iterate through, we can just add it here. So we have a list with image and then our list of images. We run this, we'll get all of those lovely images blurred. And now let's do the same thing, but this time let's use map. So we already know to blur an image, we just need to do blur of the image. So if we're thinking about using map with that, we want our function, and then we want to have map across whatever list. So in this case, it's this list of images. And if we run that, we get all of those blurred. So hopefully both of these things make sense. You're starting to see how these work. You're also starting to see where one might be better suited than the other. In this case, map was way simpler to write out than table. In other instances, table will make more sense than map. So hopefully that's all making sense, and we can move on to the next section.
In this chapter, we're going to start getting into the functions we'll need for working with visual outputs like graphics and images. We'll learn how to create and use colors within Wolfram Language, and using the graphics framework to design visuals. We'll also look at built-in functions that help us create randomness in our outputs. When we're working with colors in Wolfram Language, we've got a good starting point with the built-in color options. Not only do we have colors beyond the standard rainbow selection built in, but also pastel versions of all the colors. We can call colors by using the name of the color, though as you can see from these lists, we don't have every single color name built in. We can call red and get the color internally saved to red, but we don't have a built-in maroon or vermilion or other less common color names. To get the other shades, we can use the function RGB color, which takes a list of the red, green, and blue values to combine it to the output color. You might be familiar with RGB color if you've worked with other kinds of digital design. We also have the function hue, which is a little less flexible, but gives us the colors around the color wheel. We can input a number between 0 and 1 into hue, going from red at 0 through orange and yellow, green, blue, and purple, and looping back to red at 1. If we're sticking to grayscale, we can also use the function gray level. Gray level works similarly to hue, but instead goes through the various gray tones between black at 0 and white at 1. We also have a selection of functions to modify existing colors. Gray level can not only be used to generate a gray color from a value, but also to find the gray level of a color like magenta. The functions lighter and darker let us shift a color value without needing to alter all of the RGB values ourselves. Unlike the first three functions here, blend takes in multiple colors and combines them, so we can use blend to combine red and yellow to get orange. Another useful function is color negate, which gives the opposite value of a color. One of the big use cases for colors is within graphics. We use the function graphics to build up a visual output with different components like text or shapes. We not only have built-in colors, but we also have some built-in shapes that make it easy to get started putting together our graphics. If we only have one thing we're using within graphics, we don't need to put it inside a list, but almost always you'll have more than one thing. In that case, we need to make sure we give any graphics components within a list. So let's say we want to create a red triangle. We need to, within graphics, put a list with the color red and the function for creating a triangle. Building up this list, we can create more and more complex graphics. We can give graphics multiple different shapes, different colors for each shape, and within the shape functions, we can give specifications like size or position. One thing to keep in mind when working with graphics is that things are created or used in order, including colors or other styling options. So, if we want to add a blue disk to our red triangle, we need to first specify that we're changing the color to blue, and then add our disk to the list. If we do it in the reverse order, graphics will use red for both the triangle and the disk. Right now, we're just scratching the surface of what you can do with graphics. To cover a few more things we can do, we can create unnamed shapes with the function polygon, where we provide the vertices for the unnamed polygon in order of how they're going to connect. Including shapes, we have other graphics objects like point and line. A lot of functions within Wolfram Language not only have arguments, but also options. Options have default values, but we can change what values are used for an option. For example, graphics has a ton of options, including one for background. If we wanted to change the background from the default, we use graphics. We write out our arguments like normal. Then, before the ending square brackets, after our regular arguments, we add in our options. We indicate options with the name of it, in this case background, and then an arrow and what we want to set that option to. You can write the arrow by using a dash and then a greater than sign. The notebook interface will automatically make it into a nice looking arrow. Moving on from graphics, let's quickly talk about randomness at the end of this chapter. There's more functions for getting random outputs for different types of data than we can cover here. We've already seen the function random color in a previous section, and there's similar random functions for integers, real numbers, polygons, words, and more. One slightly different but useful random function is random choice, which randomly returns one item from a list of options. So let's say we wanted to get a random color, but only from a list of specific colors. We could use random choice to get that random decision from the list for us. We've gotten a good start into working with visual outputs in this chapter. You can now call colors in a variety of ways, either with color names, RGB color, or hue. You've also seen how we can build up complex graphics starting from a pretty simple base by listing out the components and their styling. We've also touched on how we can easily complete computations with randomness using built-in functions for different data types or making selections from a list with random choice.
Awesome. We're going to do another exercise for this section. Great. Cool. So we're going to do this first exercise here, do some stuff with colors, and also get a little bit more experience with map and table. So we want to create a list of 10 random colors, darken them all using map, and then get their opposite using table. So 10 random colors, we just learned that there's the function random color that we can use to get a random color. If we give it a number in here, it'll create a random color that many times. So that's how we can get our list of 10 random colors. Great. Step 1, done. Now we want to darken them all using map. We have a function called darker that we can use that just takes in a color and makes it darker. So we can use darker, and then we can map it onto our list of colors. And nice, that all looks like darker versions of the kind of colors we were getting before. Still nice and random. So that's step 1 and 2 done. And then we want to get their opposites using table. I don't quite know what to look for an opposite of a color. So let's try a little documentation search. And if I look this up, I'll see nothing immediately on this page, except it is showing up. We've got this down here, color negate gives the negative of a color, which is, I would say, is opposite, but let's check and see. And yeah, it's giving what the opposite of that color would be. So I want to use the function color negate. So I can build up my table. So table, and then I want to use color negate on everything, on all of those colors. So we'll use color as our variable, and then our second argument will be that variable, and then the list of things we'll iterate over, in this case, all of our darker random colors. And then if I run this, I get a bunch of, in this case, turns out it's a bunch of fun kind of pastel colors. So we've got list of 10 random colors, way down over here now, darkened, happening here, and then their opposites happening with table. Awesome. I think with that, we'll move on to what I think is the last section for today, unless there's any questions. One quick question before we start the video: where can we find these exercises? They're on that course framework. So if you go click on the little link at the top of the chat that says go to course framework, you can find the exercises in there.
In this last chapter before our first mini project, we're going to cover working with images in Wolfram Language. We'll look at how we can even get images into our notebooks, analyzing images, and editing images with different filters and effects. We've got a few different options for how we can get images into our notebooks. Just like a word processor, we can copy and paste images we've gotten from online. Another easy option is to drag images from our desktop into our notebook. Some more computational ways we can get images is with the function import, which we can give a file path. We also have the function example data, which lets us get examples of a variety of different types of data, including images. Another is to tap into Wolfram's natural language functionality, which we can do by, within a code cell, pressing Control and then equal on our keyboard to get a natural language input box. We can then look up whatever we want in this box, like an image of a tiger, and get that straight into our notebook from the Wolfram knowledge base. One last fun option is to use our webcam to take a selfie with the function currentImage. Now that we've got an image into our notebook, what can we do with it? Well, images are made up of hundreds or thousands of pixels that each have a single color. We can break down our images into those individual pixel values with the function image_data. From all those pixels, let's find the first one. The output of image data is a list of lists of lists. The highest level list is all of the pixels in the image. The second level of the list is the pixels grouped into the rows of the image, and the final level of list is the value for each individual pixel. We can use the function part and its shorthand of double square brackets to get individual pixels. So to get back the first pixel, we first want to get the first row, and then the first thing in that first row. This gives us back the first pixel. Our output is just the numerical RGB values. So to get a color we can do things with, we'll need to use the function RGB color. What if we want a random pixel? We can do it with random choice. First, we select a random row, and then a random pixel from that row. We can also reverse engineer our image from the pixel values. Let's also display just part of this image. First, we're going to create a table to get the RGB colors for each pixel in the first row. Then we take that list and display it as a row. Another cool thing we can do with images without needing to dig into image data is to use the function dominant colors directly on the image. This will let us find the most common colors of the image. We've just started to dip our toes into analyzing images, but now let's look at how we can change images. There's a lot of functions for image manipulation that are pretty practical. For example, we can use remove background to make the background of an image transparent. We can also resize images easily with the function image resize. A few more obviously practical functions are image crop and image compose. Image crop lets us cut off parts of an image. In this case, we're cutting off 100 pixels from every side. Image compose lets us combine two images by placing one on top of the other. Wolfram also has a lot of effects and filters we can add to images. These functions might seem purely aesthetic, and often they're useful in creative applications, but they can have utility in particular use cases. A few common ones are blur, sharpen, lighter, darker, color negate, and edge detect. All of these functions we can just call the function name on an image, and it'll apply the effect. Additionally, we have a function called image effect, which adds specific filters to an image. We can use image effect to take our tiger image and give it a filter like a charcoal drawing. Another cool function is image restyle. Image restyle takes our image and another image and uses machine learning to recreate our first image in the style of the second. So we can take our tiger and restyle it to look like Van Gogh's Starry Night. One last useful image manipulation function is image recolor, which lets us take an image and then change one color, let's say orange, to another, let's say purple. Before we wrap up this chapter, one important thing to note with a lot of the functions covered here is that they have optional arguments we can use to tweak how they work. For example, edge detect can just take an image, but we can also give it a second argument that tells our computer the scale of the edges we're looking for. This could be helpful for reducing noise or making sure smaller details are captured by edge detect. We've covered the multitudes of ways we can get an image into our notebook. We've seen how we can look at individual pixel values with image data, and we've seen some of the many functions we have to quickly and easily edit or analyze images. You now not only have a start to all you can do with image manipulation in Wolfram Language, but also all the skills you'll need to tackle our first mini project on computational art.
All right, awesome. So we're getting a sense of how to start working with images, and we don't have a poll for this chapter, so we're going to jump right in to a quick exercise. Now, with a lot of image manipulation stuff, we're often looking up a lot of the functions we're working with. There's a lot of super specific ones, but the ones for exercise 3 came up just now in this video. So we want to first remove the background of this image and use the results as an overlay on this image. Let's start off with removing the background. We can use the function super straightforward, remove background on an image. And if it's an image like this, where there's a pretty obvious background to it with all the white, it will remove that background, which is a little hard to see in this case, but we'll see it better once we go and overlay it over our other little Wolfram logo. And we just saw that we can use the function. It's a little bit less direct in terms of wording. Instead of using a function called overlay, we're going to use the function image compose. And we give image compose to images. So we'll watch our 2 different images in the function. And I'm going to actually flip these because I did those in the wrong order. Great. So we can see it removed that outer background from our first image and then put it on top of our second image here. You can see that nice little output.
Great. So hopefully in this session today, we learned a bunch of kind of intro to Wolfram material. And the great thing about this course is that with each section of Wolfram material that you learn, you can apply that to a project. So we have a series of projects through this course. So the one for this chapter is on computational art. And we'll go through in our final session on day 5 all of the projects. But if you want to try it for homework this time, then you are super welcome to do that. I love a good project-based course. So, go and apply those skills that you just learned to that project. Obviously, these videos, you can pause them whenever you want. You can rewind them and replay that thing. We don't spend a huge amount of time going through each kind of micro section. So feel free to, go back and forth and figure it out. And when you have questions, you can come back tomorrow and ask those questions. So thank you so much for coming today. We're looking forward to seeing you tomorrow.